Okay, so we have this example of how to use the reddening to get to the extinction and then to the distance of the star. So I gave you the observed color of plus 0.4 in the B minus V. And from the spectrum, we'd estimated that the intrinsic color was minus 0.1. So this must have been a hot star, okay, for the intrinsic color to be negative, but its observed color was positive. So the difference between these two is 0.5. So as you can see, color excess is always positive. We can then convert that into the total extinction by using this factor of 3. Okay, so just multiply the color excess by 3 to give the total extinction. So you'd be able to use this AV value to correct the observed apparent magnitude into the intrinsic apparent magnitude if you wanted to. But here we're going one step further and using the estimate of the intrinsic absolute magnitude here to get the distance to the object. Okay, so this time, again, rearrange this equation to make distance the subject. And this time we know what AV is because we've worked it out from the reddening. And so therefore we can put all these numbers together and give us a distance of 360 parsecs. Okay. So again, remember that in this formula, D has to be in parsecs and not meters. Okay, so that's how to use color excess to find the extinction. So now let's have a little, we're going to be sort of roaming through the infrared wavebands here. So the first one I want to consider is near-infrared observations. As you saw from the extinction law earlier, the extinction law was dropping as we went further to the left in that graph. So the extinction drops significantly as the wavelength increases. Now there's a good reason for that. If we think back to the physics of how the radiation is interacting with the dust grains, recall that I mentioned that the sort of largest size of the interstellar dust grains is about half a micron or 500 nanometers in size. Now, as the wavelength, so that's typical of optical light, but as we go into the near infrared, we reach wavelengths of sort of 1 or 2 microns. But those are what we would call near infrared wavebands. And then the wavelength is significantly larger than the maximum grain size. And when the wavelength gets much larger than the size of the grain that it's trying to interact with, the probability of that interaction drops. Okay, so if you like, the longer wavelength radiation can penetrate the dust without interacting much more easily. So that's why the extinction drops. So this is good if you've got a lot of dust along your line of sight, but you can't, and you want to see behind the dust and see what's there. If you move to longer wavelengths, like the near infrared, then that is very good for seeing through dust obscuration. And again, at wavelengths of sort of 1 or 2 microns, then stars, especially cool stars, are still quite bright. In fact, very cool stars, their peak output is at around about 1 micron. If you recall the Wien displacement law for a 3000 Kelvin star, then it peaks at 1 micron. So, you're at the peak of the stellar output, but also you've significantly decreased the dust obscuration. So you can see a lot further. And so yeah, just to define what I mean by near infrared wavelengths, we're going to talk about near, mid, and far infrared. So again, it's a good idea to familiarize yourself with these different wavebands. This is part of the module, is to know what wavebands are good for what type of observation. Okay. So near infrared, you can still see stars, especially cool stars, and you can see through the dust. So just a bit of nomenclature in the brackets here. Again, you don't need to remember this, but that kind of naming convention for the filters that started with U and B and V, R and I in the optical, then carries on to J, H, and K in the near infrared. And we can see that in operation here. Let's come back to this picture that we saw earlier. So this was basically an optical picture of this dust cloud, where you saw that the extinction is so high in the optical that you can't see any stars in the center of this dust cloud at all. But if we bring in K-band observations that are at 2 microns, a wavelength of 2 microns, then suddenly all the stars swim into view. We can see them there. Okay, they're highly reddened, of course, because the reddening effect is still there, but at least you can see what's there now. Okay, so this is the benefit of near-infrared observations. Basically, you can start to see through the dust. Okay, now let's keep going into the infrared now, to longer and longer wavelengths. And this brings us into the realm of where the dust grains are no longer absorbing radiation and scattering it, but actually emitting strongly their own radiation. So in order to work out what waveband a dust grain will emit in, we need to firstly think about its temperature. So I'm going to quote some values at you here, but again, I'll leave you with a problem at the end where you can kind of evaluate this for yourselves. Now, remember that these dust grains are basically now solid particles. Okay, so here the approximation that they emit a bit like black bodies is quite a good one. That's always quite a good one for a solid matter. Okay. So if you take a dust grain and put it way out into interstellar space, so here I'm talking about a long way from any star, so sort of where the atomic gas is and also the molecular gas, then dust grains will cool down to a temperature of about 30 Kelvin, because the only thing that's heating them is the radiation coming from the stars, but all the stars are a long way away. And so they drop down to temperatures around about 30 Kelvin. Now, we can apply Wien's displacement law here to get us a rough idea. So again, you could do that for yourself, but let me do it for you. So if you put 30 Kelvin into Wien's displacement law and ask where the maximum peak of the black body curve would be, it would be at 100 microns. So 100 microns is what we would call a far infrared wavelength. Okay. So just take that from me. If the dust grains are near a hot star, okay, or certainly a luminous star anyway, then they will be hotter. Okay, so this is very similar to, if you think about sort of planets and objects in our own solar system, the closer and closer you get to the sun, the more they get heated up, and so the higher their equilibrium temperature. So if you bring dust grains near to a hot luminous star, then they can get heated up to 300 Kelvin or so. Obviously you can keep bringing them nearer and nearer, and they'll get hotter and hotter. You can get them up to about 1,000 Kelvin, but after that they literally turn into vapor, what's called sublimation. So you destroy the dust grains if you get them hotter than about 1,000 Kelvin. But let's just take this canonical temperature here because it makes the maths easy. Okay, so that will peak at a wavelength of about 10 microns. Okay, and this is what we would refer to as the mid-infrared waveband. Okay, it's about 10 microns. Sometimes called the thermal infrared as well. If you've ever seen a thermal imaging camera in action, then this is the kind of waveband that it operates at. Okay, so these days you might see a thermal imaging camera at an airport because it's trying to find, looking at humans, because obviously humans are around about a temperature of 300 Kelvin, so basically room temperature, right? And so if you've got a fever, then a thermal infrared camera will show that up quite nicely. But they're also used, to look for sort of victims buried under earthquakes, to look for people who are still alive and glowing warm underneath the rubble. So again, you can penetrate through, you can see the glow with this radiation. Okay, so that's the mid-infrared waveband. So let's see that in action. So here's a picture from the NASA's Spitzer satellite. So again, this is one that many of us in the Leeds group have been using over the years. So it really kind of revolutionized mid-infrared astronomy by being the first sort of good resolution mid-infrared satellite. So what you're looking at here is a little stretch of the Milky Way, the galactic plane. Okay. And you can see all these hotspots. And you can see a lovely bright region here. So this is at a wave band of about, again, it's in the mid-infrared, sort of 8 to 20 microns. So this would be hot, glowing dust here that you can see in those glowing orange colors. And so what's going on here is that dust is being heated up because it's near a region where sort of hot, young, massive stars have recently formed. So there's a lot of dense gas and dust here, and the dust grains are all getting heated up. Okay, so that's the mid-infrared in action. Okay, so let's think a little bit more about the physics of what's going on and what's determining the temperature of a dust grain. So I've got a schematic diagram here. So this is obviously not to scale. So we've got a star in the middle here with a luminosity L, and we've got a dust grain that has a radius A here that is some distance away from the star, obviously not to scale. So what is heating the dust grain is the radiation, obviously, that it intercepts coming out from the star. So you can see that there's, if you think about the geometry here, especially if you think about the star looking outwards, what you will see here, if the dust grain absorbs that radiation, is just a sort of circular cross-sectional area here, where the radiation that would have been streaming through here has been absorbed by the dust grain. So we're going to assume the dust grain is a perfect black body to make the calculation easy. So we assume that all radiation landing on that grain is absorbed, and that's what's going to heat it up. But at the same time, the dust grain has some equilibrium temperature itself, so it will be radiating in all directions from its surface, and that is what's going to cool it down. Okay. And so when you have thermal equilibrium, the amount of energy coming in and being absorbed equals the amount of energy per unit time going out. So if we look at the geometry of this, we can easily write down a simple equation. Okay. Well, maybe it doesn't look that simple, but I'll take you through it. Okay. So we want to work out the fraction of the star's luminosity that is absorbed by the grain, and equate that with the sort of luminosity of the grain itself as it emits. Okay. So this is our thermal equilibrium equation. So we've got absorption on the left and emission on the right. So let's go through these terms. So what's this? So pi a squared is the cross-sectional area of the grain. So that's the area of the dust grain, pi a squared, that is intercepting some fraction of the luminosity from the star. And the fraction is given by the cross-sectional area of the grain divided by that entire area of the sphere here, the 4 pi d squared. Okay. So remember, luminosity through any sphere here will be constant because the light is all traveling in straight lines. So we just want the fraction that's intercepted here. So that's pi a squared here divided by 4 pi d squared here times the luminosity. And then this equation on the right should be familiar to you. So this is just basically the luminosity of a sphere with radius a, temperature 2. 4 pi a squared is the surface area because it's emitting in all directions from its surface. And sigma t to the fourth is the power radiated by a black body per unit area. So if we now simplify this down and solve for the temperature, then we get this expression here. So let's have a look at this and see what it tells us. So if we've got a grain at a fixed distance d, but we increase the luminosity of the star, then the temperature will go up. Makes sense, right? If we keep the luminosity of the star constant, but put the dust grain further and further away, so increasing d, the temperature will go down. Okay. And if you look at the temperature dependence here, it will go as 1 over the square root of distance. Okay. So that's how a grain would cool down if you moved it further and further away from its heat source. So again, hopefully that makes sense. So again, we've assumed perfect black body and all sorts of other things here, so it's only approximate, but it doesn't do too bad a job. Okay, so I want to sort of bring this together a little bit in terms of star-forming regions here. So this is the idea of where stars are being born, okay, which is very much an area where infrared astronomy comes to the fore. So as I mentioned already, if you bring dust close to a luminous object, like a star, then it will get heated up. Okay, so what situation does that occur in? Well, when stars form, I'll show you a diagram in a moment, but basically, you have these dark molecular clouds that I showed you before. They're dark because they've got a lot of dust in them. So they will collapse under gravity and new stars will form. So that brings a large concentration of dust near to a new star once it starts its nuclear fusion. So that will heat the dust up. So that means that, like the example I just showed you from the Spitzer satellite, star-forming regions are basically bright infrared sources. And this is even more true when you've got massive hot stars that are being born. Okay. So they require bigger clouds to get going. So you've got an awful lot of dust there. And they're very luminous, of course, because they're the most luminous stars when they're born. And so those give you the very bright infrared sources, especially in our galaxy, like I showed you before. So I just want to show you this sort of diagram here. So the idea that you've got a cloud of molecular gas. So remember, that's the dense gas that's up at 10 to the 10 particles per meter cubed and down at 30 Kelvin to start with. So you start with a molecular cloud if you want to look at the star forming process. Another key point here is because of the dust that's mixed in with those molecular clouds, that blocks out the sort of ultraviolet radiation that's penetrating through the galaxy from all the distant stars. And it's really the dust that allows the molecular cloud to cool down. And in effect, it actually allows the molecules to form themselves. Recall that molecules are dissociated by ultraviolet radiation. So until the dust effect sort of blocks out that ultraviolet radiation from the rest of the galaxy, then the molecules can't actually form. So molecular clouds and dust kind of go hand in hand. And that helps to cool them down. If you imagine yourself in the middle of one of those dark clouds that I showed you earlier, because of the dust extinction, you can't see anything. You'd be in the middle there, you'd get very cold because you can't see any stars. And that also enables the cloud to collapse under gravity because the thermal pressure is very low because the temperature is low. So that's what these arrows indicate here, that the molecular cloud will collapse under gravity. But that will rapidly run away and you will form a new star, or usually a new cluster of stars, as we've seen in the center here. If you form a massive star, then that will soon switch on its nuclear fusion and become very hot and start to ionize the surroundings. So this is the idea that you get a H2 region in here, okay, around the new young hot star. So you get a bubble of ionized gas in here, but throughout all of this region, there will be dust grains as well. So you'll get hot dust grains emitting in the mid-infrared in here, and then out here, you'll still have lots and lots of cold dust emitting more in the far infrared region of the spectrum. And of course, you've also got the same ways of observing molecular clouds. So you can't observe the H2, but you can observe things like carbon monoxide here at millimeter wavelengths. And you can observe the H2 region very easily at radio wavelengths. That will penetrate through the dust clouds and you can see them very easily, whereas the dust might block your view in the optical entirely. Okay. So this is the idea of using different wave bands to pick up different portions of what's going on here, whether it's the radio continuum and the ionized gas, millimeter lines picking up the molecular gas, and infrared radiation picking up the dust. Okay. And you can begin to piece together multi-wavelength pictures of the same object by using this kind of picture. So, talking about multi-wavelength pictures, let's go back to galaxies again, and go back to our old friend, the Andromeda Galaxy. So I've shown you this picture before. This is an optical picture of our nearest spiral galaxy neighbor. And here is the view of that object at mid-infrared wavelengths from the Spitzer satellite. And you can see that it's the spiral arms that are really lit up brightly in this object. Okay, and so you can see them in absorption over here. Okay, so this is the extinction effect of the dust. So this is the radiation being absorbed by the dust. But of course, that absorbing of radiation is then heating the dust clouds up a little bit. And so they start to glow over here. But more than that, it's the spiral arms where new massive stars are being formed. Okay. And so that's the hot dust here at the mid-infrared wavelengths, and all these little blobs that are joining up throughout the spiral arms here. These would all be regions where new stars are being formed. So there's a kind of a good correspondence between what's dark and black over here is glowing bright over here. So that's two sides of the absorption and the emission process. Okay. Another nice thing to note is that the elliptical galaxy neighbor here and here do not show up at all here, which confirms what we said earlier, that basically there is no interstellar dust in elliptical galaxies. There's no interstellar medium. Okay. There's no more star formation going on in these galaxies. They've basically, they're just stars. And here, I'm just switching to a far infrared view of the same galaxy. Okay. So if we can flick between the two there, okay. Again, now you see the spiral arms even more dominant in this image. So here we're really just picking up the cool dust. So this would be equivalent to mapping out the kind of molecular cloud emission in this object. So here the dust is down at 30 Kelvin. Very similar temperature to the molecular clouds, and all of those molecular clouds only inhabit really the spiral arms in these spiral galaxies. Okay, so let's summarize all of this. So the interstellar dust is responsible for extinction and reddening of starlight, basically, or nebula light, any light, at optical and ultraviolet wavelengths. If we want to see through the dust, we just need to move into the sort of near-infrared regime, where the extinction effect is significantly lower. And if we want to see the dust itself in all its glory emitting, then we need to go to the sort of mid and far infrared wave bands, where we can see the emission from either warm dust at sort of several hundred Kelvin, or cool dust down at a few tens of Kelvin. So, again, we're sort of filling out the rest of the electromagnetic spectrum here. And so here, these are the uses for infrared astronomy. Okay, so as promised, a chance for you to work out the temperature of these dust grains for yourself in some sort of realistic scenarios. So, the first scenario here is very close to a massive young main sequence star with one of these high luminosities. So work out the temperature there, and then do the same thing. If the dust grain was, a long way away from, in between the stars, basically at a parsec away, what temperature do you get then? Okay, so we'll leave that one for next time, and then we'll go and have a look at our own Milky Way galaxy as an in-depth example of our own of a spiral galaxy.